All right, so over here, I have a simple system. It's basically there's a big mass of mass M connected by an inclined pulley system to two connected particles, one of mass M and one of mass 2M. Uh, right, so the question is, first of all, derive an expression for the minimum value of capital M, so this block over here, for which the system remains in equilibrium position. All right, and the second part is after the string connecting the masses M and big M, so this string over here that I've highlighted in red, after it breaks, the blocks follow the distance d down the incline as seen over here. All right, so I want you to calculate the final speeds of the block on the incline, so these two. All right, you might be familiar with this. This was taken from AP Physics C's free response question 2019 set 2. I'm just doing parts D and E because I think they connected nicely. And if you understand this part really well, the first three parts are like really simple. So if you think you can do it, have a shot at it, and I'll show you the solutions in 1 second. All right, so let's jump into it. Part A. All right, so how will we go around deriving an expression for M? Well, the first thing to do always in like kinematics, like dynamics problem is just draw your free body diagrams, create Newton law equations. So let's do that for the first one, the big mass, big M over here, because that's like the easiest one in my opinion. It's the mass M. Now it will have a downwards force of gravity of capital Mg, and I'll have an upwards force of tension of T2. Note that I'll be T2 because the tension here is T2. So this tension here will also be T2. So I can specify that here, T2. Okay, so since it's in equilibrium, you could say that T2 minus capital Mg is equal to 0. You could even say Mg minus capital T2 is equal to 0 because the main thing you want to get out of it is that these two are essentially equal to each other. T2 is equal to capital Mg. And now this will be useful in creating our Newton law equation for the two connected particles on the incline. So let's try to make a free body diagram for that. Okay, so this is my incline here. And these are my two masses, 2M and M. Okay, so note that they are connected particles. So what can I do? Well, they will be both moving at the same speed. So they'll be moving the same speed. They'll both be moving basically synchronous to one another. So why don't we just, well, merge the particles, like visualize by merging the particles. So instead of doing this, I will draw just one big particle as such of 3M, because 2M plus M is 3M. It'll have a tension here of T2, the same T2 over here. And obviously it's going to have a downward component of gravity of 3 mg. Let's separate that out into its components. So one perpendicular, one parallel. This is theta here. So downwards here will be 3 mg cos theta. Parallel to it will be 3 mg sine theta. There is a reactive force, normal force that acts upwards like this, which is basically the same thing as the component of gravity acting perpendicular to the plane. So it will just be 3 mg cos theta. Also note that I forgot to mention it here, but the plane is rough. Okay, so it will have some sort of static friction that prevents the blocks from sliding downwards or upwards. Okay, so because it is rough, we have to take that into consideration. Let's just remind ourselves, how do we calculate friction? Friction, Fr, is equal to some constant mu, coefficient of friction, times the normal force, Fn. Because we are working in equilibrium, this coefficient will be static friction, Fs. Okay, so essentially our frictional force will be so 3 times mu s mg cos theta. it's same thing as saying mu s times 3 mg cos theta. I just like putting the number up front. Okay, so which direction will this go? Well, note that the block does want to slide downwards like this. And because it wants to slide downwards, the frictional force will act upwards. Okay, it prevents it from sliding. So I'm just going to write this here, Frx this way, and I've specified what that is here. So let us draw, like, write down the Newton law equations. T2, which is basically mg, but I'll just write that a bit later, minus 3 mg sine theta, because that's the component acting parallel to the plane, 3 mg sine theta, plus 3 mu s mg cos theta is equal to 0. Why is this again? Well, note that it's an equilibrium, no change in movement, so there's no acceleration at all. In fact, I can just go around saying that T2 is equal to 3 mg sine theta minus 3 mu s mg cos theta. Okay, let's just do some algebra here and substitute T2 for capital MG. Capital MG will be equal to, let's factor out a 3 mg to get sine theta minus cos mu cos theta, mu s cos theta. And let's cut out the g's, and we get that m is equal to 3 little m sine theta minus mu s cos theta. And that is our answer. The minimum value of m, the minimum value of m for this system to remain in equilibrium will be 3 little m, sine theta minus mu s cos theta. All right, I hope that wasn't too bad. If you did understand that, part B will be a breeze, honestly. So let's do part B. Let's just remind ourselves what the question is. After the string connecting mass at little m and big M break, so after it like cuts, the blocks follow the distance d down the incline. So they want us to calculate the final speeds of the block. So now this is just a kinematics formula. We need the SUVAT, either distance, initial velocity, final velocity, acceleration, and time. So let's think about what we need. Let me redraw the free body diagram for the two connected particles, which I'll just model as one big connected particle of 3m. 3m. Okay, after it breaks, like the moment it breaks, it's going to still be in static friction, and then it's going to go kinetic friction like just after time t is equal to 0. So it will initially have an initial speed of just 0 meters per second. So I'll just write u just to say that this is initial velocity. You can also write v sub 0. Well, that's just going to be 0 meters per second. Now, final velocity is what we're going to calculate, which I'll just call x meters per second. Now, we do have distance. The distance it falls is d meters. So s is equal to d meters. Okay, we have u, we have v, we have s. We could also probably find the acceleration using a Newton's second law equations, A. Now let's try to find out what A is. And then after that, we can connect all these without even having to use time, because that's not given to us, with the formula v squared is equal to u squared plus 2as. If that sounds unfamiliar, I suggest revising your kinematics, because this is one of the 5 basic SUVAT laws in kinematics. All right, so I'm just going to erase the d meters over here, so I just give myself more space. Okay, so if you remember from the last part, we saw that the component of gravity acting down the incline was 3 mg sine theta. I showed that up here, 3 mg sine theta. Okay, once again, because it's moving downwards, the whole system is moving downwards, we're going to get friction acting opposite to it. However, we need to be careful. This friction is not just any friction. This friction is now kinetic friction because it's moving. So it's 3 mu k mg sine theta. It's no more mu s because the frictional force is now less than the force of gravity acting downwards. We do not have any more tension on this because the tension is now broken. They're just moving together. So from this, we can basically calculate acceleration. So F is equal to mass times acceleration. The total mass is 3m. So we'll get 3 mg sine theta minus 3 mu k mg. Sorry, I wrote sine theta. I meant to write cos theta. Mg cos theta is equal to 3ma. Okay, you should be able to see that there is a factor of 3m in each of them. So there's a factor of 3m here, a factor of 3m here, and a factor of 3m here. So essentially, I can just cut them out. I cut out the g, my bad. Okay, so I'll just get that. I can factor out a g here. G sine theta minus mu k cos theta is equal to our acceleration. And now I can substitute that back in here. I'll just rewrite this g sine theta minus mu k cos theta, meters per second squared. Okay. So let's use all of this and substitute back into this equation. V squared is equal to u squared plus 2as, or v is equal to the square root of u squared plus 2as. We saw that u was 0 because at time t is equal to 0, they're still going to exhibit static friction. So just after that, it's going to be kinetic friction, which starts to move. So u will still be 0. So cut that out. So v will basically just be the square root of 2as. So that'll be the square root of 2. A is, we just saw it, it's right here. G sine theta minus mu k cos theta. And then what is, let's make this a bit smaller. What is our S? S is just D. So if we want to just clear that up, we get that V is equal to the square root of 2GD sine theta minus mu k cos theta meters per second. And here I should write kilograms just to make sure we have our units. So thank you. I hope you enjoyed this. Hopefully you understand the physics problem and hopefully you understand future physics problems you might encounter, which are similar to this, connected particles on inclined planes. So thank you for watching.